Additional circuit components that we need to consider are dependent sources. Dependent voltage or current sources provide a voltage or current that, surprisingly, depends upon some other circuit parameter. So a dependent voltage supply is going to be represented in a circuit schematic by a symbol that is very similar to an independent supply. The exception being that the dependent voltage supply is going to be represented in this diamond shape, whereas the independent voltage source is going to be represented with a circle around the plus and minus symbols here. So this symbol right here is a dependent voltage supply, and the dependent current supply is very similar to an independent current supply, except it's going to be represented again with this diamond shape around the arrow, and the arrow designates the direction of conventional current. All right, so these sources are abstractions that act like voltage supplies or current supplies that will depend upon some other circuit parameter. So for instance, if we have a circuit that looks like this, we have essentially one possible loop for current to be provided by this voltage supply that's going to pass through this resistive element here. And since this is an independent voltage supply, we know that the voltage supply is going to be a fixed constant value. And if we know the resistance value, we can calculate how much current must pass through this resistive element using Ohm's law. Over on the right-hand side, we have another voltage supply, but this voltage supply is a dependent voltage source. This dependent voltage source provides a voltage that is proportional to the current that is delivered through resistor 1. All right, so in all of the examples or all the circuit schematics that use this abstraction of dependent sources, we will have some indicator beside the voltage source as to what it depends upon and what the relationship of the dependence is. So a independent voltage source or an independent current source will have a number beside it that represents the voltage or current that's supplied, the constant value. The dependent source will have some variable representation of the dependent nature of the dependent source. So here, this voltage supply will act exactly like a dependent voltage supply, except it is going to provide half 0.5 of a voltage that's proportional to 0.5 times the current through resistor 1. So for example, if the current through resistor 1 happens to be 1 amp, this voltage supply right here will provide half a volt across resistor R2. Similarly, if this is a 10 amp current that passes through resistor 1, this will be a 5 volt supply. All right, so to look at how we can use this, let's look at another example. In this example, essentially we have two separate paths, two separate circuits. We have the one on the left-hand side right here that is driven by this independent voltage source of 15 volts, and we have a second loop that is driven by a dependent current source, and the current provided by that dependent current source is 3 times the current that is passed through the resistive element R3 right here. All right, so let's take a look at how we'll analyze this circuit and determine the output voltage across resistor R5. Okay, so again, we have essentially two separate circuits here. So what we will do is we'll use the concept of equivalent resistance to analyze this circuit first to determine how much current passes through resistor R3. Once we know how much current passes through resistor R3, we'll know the amount of current that is provided to this part of the circuit by the dependent current supply. Once we know the current that's provided by the dependent current supply, we can use Ohm's law to determine the potential difference that's developed across this 720 ohm resistor R5. Okay, so to begin with, let's look at how we're going to use the concept of equivalent resistance to look at this portion of the circuit on the left. All right, using the equivalent resistance, we know that we can combine R2 and R3 into an equivalent resistance because since they will both have the same potential difference across them, they will be in parallel with each other. So parallel resistance elements can be combined using the reciprocal or the inverse reciprocal addition. So this combined R2,3 equivalent resistance is going to be the inverse of 1 over R2 plus 1 over R3. Right. When we crunch through the numbers, since R2 is 2,200 ohms or 2 kiloohms, and R3 is 1 kiloohm, when we do this math, we wind up with an equivalent resistance of 687.5 ohms for the equivalent resistance of R23. Now, this is a little trick or a little thing to be aware of, that when we add elements in parallel, when we add these resistive elements in parallel, the result that we get should always be smaller in resistance than the smallest element that we're adding in parallel. So here the smallest element is 1 kiloohm, and that's being added in parallel with this 2.2 kiloohm resistor. And the result of that addition is, the reciprocal addition is 687.5. It's a lower overall resistance, overall combined resistance, and that kind of makes some sense if you think about this in terms of the water analogy. We have two restrictive paths for water to go, or for liquid to flow through. And since there are two possible paths, the combination of those two paths provides a wider area or less restriction to the flow than looking at a single resistive element or a single pipe. All right, so in that case, since we're combining these two in parallel, it's going to look like there's less overall resistance in that path. Okay. Up here, we remember that R1 is still a 1 kiloohm resistor. We can combine those two elements in series with each other because they see the same current through both of those resistive elements. All right, so combining those in series, we get our equivalent resistance, or our equivalent circuit, that looks like a single 15-volt power supply in series with a 1 kiloohm plus 687.5 ohm resistor, or a 1,687.5 ohm resistive element. Now that we have the equivalent resistance, we can calculate how much current is delivered by this voltage supply to this closed loop. All right, the total current that's delivered is going to be given by Ohm's law, and by rearranging Ohm's law, we know that the voltage, that current is going to be the voltage across the resistive element divided by the resistive element value. All right, so that will be 15 volts divided by 1,687.5 ohms, which gives us a current value of 0.008 repeating. Right, and I'm going to truncate that there, carry in a few extra significant digits to make sure our calculations are precise. All right, from that point, once we know the current through this equivalent resistance, we know that that current is going to be the same both through R1 as well as through the combined R2 and 3. So now we can determine the potential that's developed across the R2,3 equivalent. Right? The potential difference, or the voltage that will be developed across this resistive element right here, which will be the same as across R2 and R3, will be given again by Ohm's law. So the voltage across the R2,3 equivalent is going to be the current times the resistance of the combined R2 and 3. All right, so we're going to take this value, this current value, and multiply it by 687.5, and when we do that, I get a value of 6.111 repeating volts. Okay, now that we know the voltage that is developed across the R2,3 equivalent, since R2 and R3 are in parallel with each other, we know that the potential difference across R3 also has to be 6.11 volts. Right? With that information in hand, we can also calculate how much current passes through resistor R3. All right, so again, rearranging Ohm's law, the current through R3 is going to be given by V over R3, and it's going to be the voltage across R23 equivalent. So 6.11 volts divided by 1 kilo ohm is going to give us a current value of 0.006111 repeating amps. So now we know how much current passes through this resistive element, right? And the current that's provided to this loop of the circuit right here depends upon the current that's passed through this through the resistive element R3. Right? And we're told that this dependent current supply provides a current of 3 times the current passing through resistor R3. Right? So 3 R3 is going to be 0.01833 amps. Okay? So now that we have that in hand, we know how much current is being supplied to this loop right here. The relationship between R4 and R5 is that they are in series with each other. So since they're in series with each other, both R4 will have a current of 18.33 milliamps passing through it, as well as R5 will also have 18.33 milliamps. So now, in order to calculate the voltage or the potential difference that is developed across the resistor R5, we employ Ohm's law yet again. And we can determine that the voltage across resistor 5, which is the same thing as the output voltage that we are looking for, is given by this current value, which is 3 times IR3, multiplied by the resistance of resistor 5. Right? So that is 0.01833 amps multiplied by 720 ohms. And the product of those two values is going to give us a value of 13.2 volts. Right? So from this analysis, we've determined now that the output voltage is 13.2 volts across this resistive element right here, R5. And that resistive element was driven by this dependent current supply, and the dependent current supply provided a current of 18.33 milliamps, and that's because this current supply was dependent upon the current through resistor R3. And the current supplied by the dependent current supply was 3 times the value of the current through resistor R3. So we've coupled these two circuits, these two loops together through this dependent supply. In the future, we're going to use these dependent supplies to help us model or come up with abstraction models for common circuits and instrumentation components that we would not easily be able to model directly from the physics. So this provides a mechanism by which we can more easily analyze some common circuit components like operational amplifiers, transistors, field effect transistors, and things like that.